is John Garner, and this is my presentation, Separation of Polylactide-co-Glycolides using Semi-Solvents, a tale of many polymers in one. Before I begin, I'd like to briefly introduce Akina Incorporated. Akina Incorporated is a company based in the Purdue Research Park, provides both research supplies through the Polysci-Tech division, as well as analytical services through Acknowledgements. In the Polysci-Tech division, we have over 650 different products available based on a variety of PLGA, PEG-PLGA type block polymers. From these products, over 450 research publications have been written. In the Acknowledgements division, our primary focus is on providing contracted research analysis as well as analytical characterization of PLGAs and drug delivery systems. Now, briefly introduce PLGA. This is a copolymer. It's biodegradable, biocompatible, has been around for a very long time, since the 1970s, has used widely in clinical applications, ranging from sutures to microparticles for drug delivery systems. The primary properties of any given PLGA polymer can be assayed by a variety of techniques. These have already been established previously in literature, including HNMR by comparing the peak at 5.2 versus 4.8 parts per million to obtain lactide-glycolide ratio. Gel permeation chromatography can be utilized to obtain the number average and weight average molecular weight of PLGA. The end cap of PLGA, whether it's an ester or an acid end cap, can be determined using either C13 NMR for small sample sizes or total acid number for larger sample sizes. The shape of PLGA, if it is a branched or star-shaped polymer, can also be determined using gel permeation chromatography with multiple detection, including viscosity. Additionally, the chirality of PLGA in terms as it applies to the lactide portion of it. That can be determined for higher lactide content PLGAs, typically above 60 to 70% lactide content, by looking at decoupled NMR and looking at the properties of PLGA, which are a little bit more difficult to determine. One of those is the lactide dispersity. So we are well familiar with the molecular weight dispersity of PLGA, where we have shorter and longer chains. There's also a dispersity of the lactide content on the various chains, and I'll be talking about that more detail later. The blockiness versus randomness. We can utilize C13 NMR to determine the RCMS by looking at the glycolide carbonyl in terms of determining whether it's adjacent to another glycolide or another lactide. And this can give us a relative measurement of the blockiness. However, it doesn't really provide for exact sequencing of the lactide and glycolide units. Additionally, semi-crystallinity. So when PLGA forms, you tend to have glycolide blocks, which I will discuss here. And those can have the ability to I'll be starting with the glycolide blockiness and discussing how that occurs. So in this example, we're showing a typical PLGA reaction, in this case, performed in a round bottom flask. In order to generate PLGA, we're working with the dimer monomers, lactide-glycolide, and usually catalyst, in this case, stannous octonate. When you combine these monomers with this particular catalyst, usually the reaction is performed as a bulk melt polymerization. And in order for the reaction to get going, the respective monomers have to be heated up to where they will melt. The problem is that glycolide and lactide have very different melting points. So glycolide tends to melt in the 80s of degrees Celsius range. Lactide tends to melt in the 110 degrees Celsius range. So in this case, then usually the glycolide will effectively get a head start on the reaction, simply because of its melting point. Furthermore, the enthalpies of the reaction, it is an exothermic reaction of polymerization. They're quite different between polyglycolide and polylactide. It has been established in literature, polyglycolide has a significantly more enthalpic reaction. And a large part of this is also driven by the self-crystallization, which occurs with polyglycolide chains, as they tend to affiliate quite closely to one another. Because of these reasons, you usually end up with, in the early stages of a PLGA reaction to form, areas that are very highly rich in glycolide. Now, it's not all bad news, because transesterification also occurs during PLGA reaction, in which the forming polymer chains will interact with one another. And this will break up the glycolide blocky regions a bit and provide for some increase in randomness. However, the reactions that occur here are overlapping and they're occurring simultaneously. So inevitably, there will be within any given PLGA some regions that are higher in glycolide than in other regions. And this is very important in terms as it applies to solubility, because these glycolide-rich regions, there's a great deal of polymer chain-to-chain interaction. They have a good steric conformance, and they tend to form into crystalline domains, which are very difficult to break up by organic solvents and strongly affect how the polymer behaves as it is used in a variety of different applications. So as I described, because of these competing reactions, we end up with a dispersity of lactide contents. Some chains have higher lactide than others. Now, we're very familiar with dispersity as it applies to molecular weight. In this case, we have worked with gel permeation chromatography for a long time. We can utilize number average or weight average molecular weight. And then between those two, because of the weighting averaging that occurs in those, typically number average is less than the weight average molecular weight. And comparing those can give you an idea as to the dispersity of the PLGA relative to its molecular weight, simply the chain length. Presumably, as we know, lactide will have a dispersity along the chain. Some chains will have higher lactide or lower lactide. Then there will be a way to determine whether or not there is a high dispersity of lactide content in any given PLGA. Now, we can't get that directly from lactide measurements performed by H&MR as they are now, because H&MR, by its very nature, only provides the general average of all the polymer chains combined within any given sample. And so in order to be able to determine the lactide content of the PLGA chains and the dispersity between those, we will need a way to separate out the PLGA of higher lactide content with lower lactide content PLGA in a manner similar to what is done by gel permeation chromatography, which acts to first separate out higher molecular weight PLGA chains away from lower molecular weight PLGA chains. Previously, we have discovered a wide variety of solvents which display what is referenced as the semi-solvent effect. In this case, as it applies to PLGA, there are a series of different solvents, some of which are listed here from one of our prior publications, which have this ability to dissolve PLGA selectively. They can only dissolve PLGA with a higher lactide content relative to low lactide PLGA. And these can be used potentially as a way to separate out PLGA chains from one another, even when they're combined together in mixtures of PLGA of high lactide with low lactide. Now, one of the questions that's inherent to this, of course, is what is driving this semi-solvent effect? And we'll explore that here for just a little bit as we get into this, because as you see, there's a wide variety of solvents here, which don't necessarily, right off the top, appear to have a significant relationship to one another. When we first started investigating this, one of the aspects to check into is simply, is this driven by the solubility parameters between this? Are these simply solvents which have better solubility for polylactide relative to solubility for polyglycolide? And by themselves, Hansen's solubility parameters do give at least an idea of which solvents can have a solubility for PLGA, but they don't really seem to tell the whole story because not everything lines up exactly the way, according to Hansen's solubility predictions, would lay out for these types of materials, these types of solvents. This seems to indicate that there is some other factor at play with the semi-solvent effect as it applies to the PLGA solvation of higher lactide versus lower lactide So we've been investigating that lately as well. And in this case, one of the trends we've noticed is that ketones and esters, in terms of as classes of solvents, typically exhibited reduced solubility with increasing alkyl content. So the longer the ketone chain was, the longer the ester chains were, the less solubility they exhibited for PLGA, and they required a higher amount of lactide to be present in order to dissolve any given PLGA chain. We decided to check into this a little bit more to see if perhaps there is some kind of a correlation simply between the solvent size relative to its ability to dissolve PLGA. And this is part of the data from a scientific poster, which is also being presented this year at CRS. And what we have here is 6-carbon esters and ketones. In terms of the chemistry, these solvents are very similar. So we look at a caprolactone, butyl acetate, propyl propionate. These are actually the same number of carbons, same ester group. The only difference is the configuration. And in these cases, we have found a seeming correlation between effectively the size of the solvent molecule versus its ability to dissolve lower lactide content PLGAs. However, this has led us to have a bit of a working hypothesis in terms of one of the driving factors for the semi-solvent effect, which may be related to the formation of the glycolide-rich crystalline regions. And in this case, we hypothesize that there is the potential for the solvent to be able to enter into these glycolide-rich regions, may be part of what is driving this relationship to the solubility of PLGA of a given lactide content in a given solvent. Notably for hexanone ketones, cyclization, so essentially when we're forming into a cyclic molecule, has a significantly higher solubility for PLGA compared to either the linear or isomeric forms of that same ketone. We're still collecting data on this to get a further understanding. However, this provides a little bit of background for figuring out ways to use, not only find more semi-solvents, but also to apply the semi-solvents we have now. And in this case, our goal is to be able to take a PLGA from a singular batch and start figuring out ways to separate it out. Now, we know GPC, of course, can be used to separate PLGA based on its molecular weight of each specific fraction of the PLGA. However, using semi-solvation, we also have the ability to now separate out PLGA, not just by molecular weight, but also by its either blockiness or its lactide content relative to the main batch of the PLGA. And in this case, what we'd be using at this stage is semi-solvent fractionation. So as a brief sketch here to explain, semi-solvent fractionation is just taking a singular set of PLGA and exposing it to a sequence of solvents. In this case, we're working with, roughly speaking, these various solvents have different cutoff points along the PLGA lactide-glycolide ratio in terms of their solubility. And in this case, we're working effectively from toweling backwards. So we're collecting the higher lactide content fractions and then sequentially washing the PLGA with solvents that allow for lower lactide content solubility and collecting each fraction as we go. And this is, we have applied this previously in terms of working with mixed polymer batches where we had mixtures of different types of polymers. And we've also applied this in terms of taking a singular polymer batch and separating out the various components of that PLGA batch. As we're working with this, we've been able to collect from a variety of different PLGAs, different polymers, fractions of different lactide-glycolide ranges. So in this case, when we're working with these, we can separate out the high lactide range using the toweling, and sequentially from each one further down, collect up different fractions of lactide-glycolide ratio PLGA from the singular batch. And this way we can fractionate it out. Now, we don't necessarily have a convenience quantitative measure for this, such as number average or weight average lactide content. That exists for GPC. So to define the dispersity in lactide contents, we've been working with as a way to quantify this. It essentially is treating it as you would a standard deviation. So we're operating on the assumption that the first NMR provided of the batch as a whole provided essentially the average of all the fractions combined, which is a reasonable assumption. And then as we're sequentially removing fractions, we're taking the mass of each fraction relative to the composition of the whole sample, as well as the NMR determined of that fraction lactide content. And then we're treating that essentially as a standard deviation. So we're doing the sum of differences in terms to define this as a deviation of the lactide content. And it's not exactly. And as we've been working through these various PLGAs, one of the things that we have noticed, of course, is that the method of synthesis matters. So previously, I showed some slides related to the transesterification, the glycolide reaction, the way in which the glycolide and lactide tend to be separate. And these various reaction parameters, of course, are all occurring at the same time. However, their various rates of reactivity are strongly affected by the conditions under which the reaction is occurring. And we're still working through several of these. Hopefully to have some kind of a tool to be able to demystify some of the existing questions around the various PLGA batches as to why certain batches will perform better than others under similar conditions. As we're going further, we're taking a variety of materials and we're separating. In this case, it's a relatively simple fractionation. We wanted to see what is the relationship not only to lactide content, but also to RCMS. And in every single case, when we're dealing with the soluble fraction in a semi-solvent, it is not only the lactide percent which increases, but also the RCMS. So essentially the randomness of the sequencing of lactide and glycolide. And this makes sense in terms of being able to separate out regions which are glycolide-rich, semi-crystalline, and have relatively poor solubility compared to the rest of the PLGA batch. This fits well within what our expectations for that. Furthermore, we went through a wide variety of polymers, and in this case, we're separating out materials in larger quantities and washing them to collect fractionations of specific PLGAs, which have somewhat more narrowly defined lacto deviation. And we characterize these not only against lactide percent and RCMS, but also in terms of the molecular weight. And we actually found, interestingly, some fractions where there was some differences between the molecular weights of the different fractions which were able to be collected based on their solubility, as well as their lactide percents and RCMS. In this set of data we are working with, we're customizing the semi-solvent based on the NMR determined LAGA ratio of the original mixture. And ideally, you want to use a semi-solvent that's pretty close to, with a cutoff that's pretty close to the lactide-glycolide content of the original PLGA mixture, and collect either the insoluble or soluble fraction of that particular semi-solvent. One of the interesting polymers we did have a kind of unique result around, and I'll draw your attention to this very bottom of this table here. We actually had a 95%, 5% lactide-glycolide. This is already pretty high lactide content PLGA. We did perform a toluene separation on that particular polymer. And we collected two fractions from it, one of which was soluble in toluene, the other was insoluble in toluene. And the toluene soluble portion had the same lactide-glycolide content determined by HNR, but it had a much higher RCMS based off of the C13 NMR spectrum. In this case, we are considering that we actually are working with separating away under that condition, not just based on lactide content, but actually the glycolide-rich regions. So we're essentially separating out the PLGA based on its sequencing of lactide and glycolide. This is something we continue to pursue and hopefully to gain a better understanding of this effect as it applies to the PLGA sequencing as well as its lactodeviation. So in conclusion, PLGA is a more complicated polymer than what we consider it to be. We normally consider it to be a fairly conventional polymer. It's been around for a long time. The lactide and glycolide content of it, we normally consider that just simply be a number that is described, as well as its either molecular weight or its inherent viscosity. And these are different methods or different techniques for measuring properties around the overall average of PLGA. However, I think we need to also consider, of course, what are the finer points of the PLGA in particular batch. In terms of a singular batch, we need to consider as well what is the kind of molecular weight dispersity, what is the lactide dispersity, what is the sequencing? Is certain parts of the PLGA have higher glycolide blockiness? How is that affected by the reaction conditions used for forming it? It's worth keeping in mind that several of these semi-solvents, such as benzyl alcohol, methyl alpha ketone, and several others, are also processing solvents used in the formation of microparticles. And in this case, we need to consider what is the effect of these solvents relative to the PLGA used to make these microparticles. How does that affect the particle's activity in terms of how do the particles interact with the drug, with the water as it's forming into the particle itself? And all of this ultimately, of course, controls the drug release kinetics of the PLGA microparticles used in long-acting injectables. So in order to accomplish this, we're still working for understanding the separation fractionation of PLGA based on sequencing, based on lactide contents, in order to analyze discrete components of PLGA within a PLGA batch. All these methods, of course, can be applied to PLGA microparticles once the polymer has been extracted out from them. And this analysis can be used to gain a better understanding of the PLGA formulation as it applies to the drug release kinetics, but also in gaining an understanding of these batch methods, as well as what is the differences between these polymers that at first sight, when looking through the various typical analysis, appear to be highly similar. I'd like to acknowledge the support of the Food and Drug Administration Office of Generic Drugs. They have been working with us for quite some time. They have provided resources for this and for other research activities as listed here. As well as I'd like to remind everyone that the contents of this presentation is the view of the author. Does not necessarily represent the official views of the Food and Drug Administration. And with that, I would like to conclude my presentation and thank you for your attention.